Hello, we will continue our study about damped oscillations. We saw previously in the previous videos what is damped oscillations. We said that whenever you take an oscillator and place it in any medium, the medium is going to oppose the motion. The medium is going to oppose the motion, and hence you will not have undamped oscillations, or you won't have free oscillations. The medium will provide some kind of viscosity or friction which will oppose the motion, and the result will be slowly you will see that the oscillations die out. Then we also saw what is the differential equation of damped oscillations, and we also saw the solution for damped oscillations, that the displacement of any damped oscillator at an instant t is given by a, which is its amplitude, but now the amplitude does not remain fixed, so this gets multiplied by a factor of minus RT by 2m multiplied by sine of omega d, which is the angular frequency of damped oscillations, d for damped, multiplied by time plus some phase constant, some epoch, that is phi. Okay, this is what we already derived. We also studied 3 different cases of over damped motion, under damped motion, and critically damped motion, so on and so forth. Today we want to continue with our mathematical analysis of this damped oscillations, and especially we are going to study under damped motion. We are not studying over damped or critically damped. We are studying under damped motion, which is the only motion, if you remember, which is the only motion which allows for oscillations. Over damped motion, there are no oscillations. Critically damped motion, there are no oscillations. Only when it comes to damped oscillations do we have oscillations. Now, how does this function look if we plot it? It looks like this. It looks like this. So basically, if it is starting from 0, you displace your oscillator, it goes to some point, it travels to some point, that means it is displaced. Then it comes back to the mean position, and now it will go on in the other direction. And then it will again come back to its mean position, then it will go on in the other direction, and so on and so forth. But the difference this time will be that the amplitude will go on reducing. Okay, so this amplitude A1 cannot be equal to A2. A1 is not equal to A2, A2 won't be equal to A3, A3 won't be equal to A4, so on and so forth. So what we studied last time is the amplitude is going on decreasing. And why is that happening? That is happening because of this term. The amplitude is not just A. Now the amplitude is A into e raised to minus RT by 2m. A into e raised to minus RT by 2m. So the amplitude falls by a factor of minus RT by 2m. That's why this yellow colored line, if you can see this yellow colored line that I have drawn, this entire sinusoidal curve is falling according to this yellow colored line. So you can see that there is some kind of a yellow envelope which shows how the amplitude is falling, and this is given by A into e raised to minus RT by 2m. Now there is another point that I want you to see. If you remember the frequency, for damped oscillations, nu d was equal to 1 over 2 pi square root of k by m minus r square by 4m square. Now if you see, everything in this term is constant. The amplitude is changing, the frequency reduces compared to free oscillations, but the frequency is constant. So a very important thing to note is that your frequency is constant. Though this frequency is less compared to free oscillations, but the frequency is still constant. That is why, if you notice carefully, this curve, the time period remains the same. See, the time that it takes for it to complete one oscillation is same when it comes to the second oscillation, is again same when it comes to the third oscillation. So the frequency and therefore the time period both remain constant. The time period remains constant and the frequency remains constant. Now we want to find out, is there any kind of relationship between these amplitudes? And there does exist a relationship. Let us try and go through a very short derivation in order to find out what this relation is. Okay, so what I'm going to do is, I'm going to start by assuming that let A1, A2, A3, A4, so on, these are the successive amplitudes. And which case are we considering? We are considering, this is amplitudes. We are considering damped oscillations or under damped oscillations. These are the successive amplitudes. Let us try and write the amplitudes one by one. The first amplitude has to be A1 is equal to some constant A multiplied by e raised to minus RT by 2m. Okay, now I'm going back to this diagram. See, this amplitude will be A into e raised to minus RT by 2m. That makes sense because this is the whole amplitude. Now, what do you think will be the second amplitude? What do you think should be the second amplitude? See, the time required for the first amplitude, see, this time should be half of the time period. This entire time should be the complete time period, isn't it? So this is half of the time period. This is half of the time period. This is this is the whole time period. So if this small t by 2 is equal to t, if I call this as t, then this capital T should be t plus t by 2. That means the next amplitude comes when you add half of the time period in the previous time. Whatever instant, let's say at 5 seconds, you got the first amplitude. The next amplitude will occur at 5 plus the time period divided by 2. Okay. So I hope you have followed the logic. And so I'll write the second amplitude A2 will be A into e raised to minus r. Instead of t, I'm going to write I'll write small t plus capital T by 2 whole divided by 2m. Okay, because I'm going to need this further, I'm going to simplify this right now. So I will write a into e raised to minus r, I'm opening the brackets, rt by 2m plus, or rather minus, r into capital T by 4m. If you see, open the brackets, this is what you get. And since this is exponential function, I can also write this as a into e raised to minus rt by 2m multiplied by e raised to minus r capital T by 4m. Okay. Similarly, can you guess what will be the third oscillation? The third amplitude will be a e raised to minus r small t plus, see, you add half time period for every successive amplitude. So if I add t by 2 here I should add capital T divided by 2m. So I will get a into e raised to minus rt upon 2m minus r capital T by 2m. So again, if I split it, I will get a into e raised to minus r small t by 2m multiplied by e raised to capital R capital T by 2m. Please make note that t is the instantaneous time, whereas capital T is the time period. T is the instantaneous time. Similarly, we'll do one more just for practice and because we can use it in the derivation. What is A4? A4 will be a e raised to minus r small t. For every successive amplitude, you add half time period. So half t plus half t should become 3t by 2. You should add 3t by 2 divided by 2m. So open the brackets again, you will get a e raised to minus rt by 2m minus 3r t by 4m. So again, split this, a e raised to minus r t by 2m minus e raised to minus 3r t by 2m. There should be no minus sign here. I'm sorry. There should be no need for minus sign. We are just multiplying this. Okay. Now, let us take the ratio of any two successive amplitudes. Okay. So, let us take the ratio of any two successive amplitudes. So, let me take the first one. A1 upon A2. What do you think we will get? If I have A1 upon A2, I should have, see, this is how we started the derivation. Now, let us just go further and see what do we get. A1 upon A2 should be, I have A1. So, I'll write A into e raised to minus r small t divided by 2m divided by, I also have a2. So let me write down a2. A into e raised to minus small t by 2m multiplied by e raised to minus r t by 4m. Okay. This is what I should get. So if I write this further, if I simplify this further, I think these two terms will cancel out. The a cancels out, the e raised to minus rt by 2m cancels out, and finally what we are left with is e raised to, this is in the denominator. When this comes to the numerator, the minus turns to plus. The minus goes to plus, so this will become rt by 4m. I hope this makes sense. Let us try one more. Let us try with a2 and a3. Again, the numerator will become a e raised to minus rt by 2m, e raised to minus r capital T by 4m divided by a e raised to minus rt by 2m, e raised to minus rt by 2m. Again, these two terms cancel out. This whole term cancels out. what we get is the ratio of this two. If you take the ratio, this should become e raised to RT by 4m again. So if you notice carefully, this is minus RT by 4m. When this comes up, this will become plus RT by 2m. So minus into plus, minus plus becomes minus. You take the subtraction, you'll get this. Now, what is A3 by A4? Can you guess? If we got this same, I think we can directly write as e raised to R into T by 4 into m. E raised to R into T by 4m. What pattern are we seeing here? What we can say is, we can generalize this statement and say A1 upon A2 is equal to A2 upon A3 is equal to A3 upon A4 is equal to so on and so forth. All these successive amplitudes, the ratio of the successive amplitudes is always going to be e raised to R T upon 4m. Now, R is a constant, T is a constant, 4 is a constant, m is a constant. E raised to a constant becomes a constant. That means the ratio of any two successive amplitudes is always going to be a constant. So what will be the, can we predict the two amplitudes? Yes, we can. Can we also know the ratio? Yes, the ratio will always be e raised to capital RT by 4m. Now, I'm going to do a slight modification here. I don't want this e raised to. So when I don't want the exponential function, what we do is we just take the logarithm. So let me take the natural log of A1 by A2 is equal to log of A2 by A3 is equal to log of A3 upon A4, so on and so forth, and finally we will get RT by 4m. Now this particular quantity that remains constant is very important quantity, and we call it lambda. So this lambda is nothing but, this is defined as the logarithmic decrement or log decrement for short. So this log decrement lambda can be defined as a very simple definition. The natural log of any two successive amplitudes in damped oscillations. Okay, we did some kind of mathematical analysis and we got some kind of quantity that is constant. Is this useful? Is log decrement really useful to us? The answer is yes. Log decrement is extremely useful. Why? Just think of what is lambda. Lambda is log of A1 by A2, isn't it? Any two successive amplitudes. I'm just taking one for example, and this is equal to R into T upon 4m. Now think carefully of the quantities that are involved. Okay, let's think carefully of the quantities that are involved. Can I find out the amplitude in any physical system? Very easy. Just use a scale, find the amplitude. I can find A1, I can find A2. Can I find the time? Yes, I can just use a stopwatch. I can find time, the time period. I know what is 4 is a constant, and I can measure the mass. What is the quantity that is missing? R. R is not always very easy to find out, and the simplest way to find out the damping coefficient is by finding out the log decrement. See, you can find out the LHS very easily. Log decrement, you know how to take logarithm. You can calculate A1, you can calculate A2. You can find out the time period, just measure it for 5 oscillations, 10 oscillations, measure the mass, and just by doing all this, you find out the log decrement. By the log decrement, you can easily find out R for any system. Now remember, what is R? R is the damping coefficient, and damping coefficient might either be viscosity or it might be friction, and R can be found out extremely easily just by using this quantity log decrement. That is why this is important. Any term in physics becomes important because of its value that we can calculate easily. So this log decrement is special because using this value of lambda, which is quite easy to calculate, using this formula, you can find out the damping coefficient. In fact, there is a very famous method called as Mayer's method to find the viscosity of any liquid. What they do is they take any liquid, immerse a disc in it, and give it torsional oscillations, and then find out the log decrement. Of course, the formula is slightly modified because it is an experimental procedure. It is slightly modified, but when you find the log decrement using this formula RT by 4m, you can find the viscosity of any liquid. So this log decrement is of great practical value. That is why we find out. I hope this derivation was clear. The derivation is very simple. Start with the, you know what is the displacement at any instant. Take just the amplitude part. Write down 4 successive amplitudes. Remember, every new amplitude, suppose you have A1 is equal to something, A2 will be, you have the next amplitude at t plus t by 2. Next amplitude A3 will be at t plus capital T. Next amplitude will be t plus 3t by 4. 3t by 4. 3t by 2, sorry. And so on and so forth. You just write down 4 amplitudes, take the ratio of any 2 successive amplitudes, and very soon you will get the log decrement. Because I don't want the exponential function, I take the natural logarithm. Very easy method, very easy derivation. Please practice this, and this is extremely useful. Why? To find the viscosity or to find the damping coefficient. The easiest method to do it is find the log decrement. That is its physical significance as well. Okay, so we'll stop here.